So welcome to Math341, Stat 341, Lecture 8. This is going to be a far more standard lecture than a lot of the previous ones. Unfortunately for you, for my earlier class today, problem solving, I had to be in a mindset where I would not remember what to do algebra-wise. So I have only had about an hour's sleep. That was the best thing I could do to try to get myself in the right mind frame for that. Worked well for problem solving. I'm not sure how well it's going to work here, so please be watching the algebra very carefully today. What I want to do is do some of the more standard material today. What we're really going to be doing is finishing up the combinatorics section of the book in the next day or two. And that means we'll be ready for an exam. So I'll be sending you information as to when the exam will be. Unless you tell me otherwise, I will drop your lowest midterm. All right? How many of you have ever played bridge? Card game. Right. If anybody's ever interested in learning how to play bridge, I have taught students in the past how to do this. It's a terrific game. A lot of great mathematics is in it. There is a standard deck of cards. There are 4 people, and you deal the cards, so each person has 13. And typically, one suit becomes a special suit in that hand. It is the trump suit. And it becomes very important to know how many trumps do you have between you and your partner, and how many do the other people have. So imagine your team has 8 trump cards. Other side has 5, because there's 13 total. It's extremely, yes?
So, do you know spades?
Yes.
So is this different in the fact that you can actually dictate which trump suit?
Yes.
And is that
You bid. The bidding is extremely complicated.
But how do you determine, okay, it's worth this time?
It's from the bidding. So I don't want to go into the details of bidding, but one suit is selected to be trump, or you could play a no trump.
Okay.
And then for this analysis, we will assume that there's one suit that's trump. We'll say it's hearts. How many hearts trump? I think that's what I do in the book. And you want to know, of the 5 cards that you and your partner don't have, how are they distributed among the other people? So it could be 5-0-0-5. It could be 4-1-1-4. It could be 3-2-2-3. Those are the only possibilities. It turns out it's often very bad for you if one person has length in trump who's not on your team. So you are concerned with a 5-0 split. And I'm going to give you 3 possibilities as to what is the probability that there's a 5-0 split among your oppositions. This is leading us into the notion of conditional probability. I know that the opposition has 26 cards split into 2 hands of 13, and I know that there are exactly 5 trump cards among those 2 hands. So I want to know, given that there are only 5 trump that I'm missing, what is the probability that one of the 2 hands has all the missing trump? So you can hear the words that indicate that this is going to be a conditional probability. Given this, okay, well, here's one possibility. There are 2 people, or 2 choose 1 ways of choosing which person gets the 5 trump. They have 13 cards in their hand, right? 5 of them have to be trump, so I have to give them all 5 of the trump. Now, how many cards are not trump? Of the 26 cards, how many are not trump? 21. And how many cards must I now give the person who's getting the 5 trump? 8. And then I divide by the number of ways to give 13 cards to one person and 13 cards to another. Well, if I give the first person 13 cards, there's 26 choose 13 ways of doing that. And now for the second person, their hand is forced. They have whatever's left over. So this is one way to calculate the probability that one person has 5 trump. And I don't care which opposition member has it. Here's another way. Method 2. There are 26 cards, right? 5 of them are trump. And the trump card could go in either hand. right? What's the probability the first trump card goes to the first person? So 1/2, right? I'm going to write that as 13/26. And again, I'll have to multiply by 2 because there's 2 ways of choosing which person gets the trump cards. So I've now chosen the first card of my first play to be one of the trumps. Now I've got to choose, I've got my next card. What's the probability that it goes to the first person, given that I've already given them one card that's a trump? Yeah, it seems 12/25 seems very reasonable. There are 25 slots remaining for me to put down the next card. If all of those slots are equally likely to get the card, then the probability that I give it to somebody who got that first card at that first hand, 12 of the 25 slots will work. I now take my next trump card. How many slots are left? There are 24 slots that are left, and 11 are left in that first hand. And then 10 out of 23, and then 9 out of 22. And again, divide by 26, choose 13. That's the second way to calculate. The third way to calculate is to say, this is ridiculous. We are making this far too hard. There's 2 choose 1 ways to choose which person gets all the trump. What's the probability somebody gets a trump card, a specific trump card? What's the probability that I've got 2 people? What's the probability somebody gets one of the trump cards?
5.
Well, I've got to assign the trump card to one of the 2 players. What's the probability player 1 gets it? 1/2. Does it matter which card I'm talking about? No. So it's just 1/2 to the 5th. So here are 3 different ways to calculate. Yes?
For 2, do we need to divide 26/13 in the end?
Oh, no, you're right. We don't need to divide by 26/13. I'm sorry, you're right. Thank you. All right, so here are 3 different ways of calculating. Do you think they're all the same? What could you do to try to see if they're the same? We could actually calculate them. The first one comes to about 3.913%. The second one comes to 3.913%. It's actually the same value. And the last one is exactly 6.25%. We know at least one of these methods is wrong. We could try to do a math analysis, but what else could we do to try to get some idea of which is right? Yes?
In the last class, you the sums of the tops of the binomial
Right.
coefficients and the bottoms. You notice that 5/21 is 26?
Yep. So that, I mean, this is definitely a very strong supporting argument for this. Yes?
You could suspect that because 2 different methods give you the same answer, that we would hope that this is the right answer.
You could hope, but run a computer simulation. Your default should be, let me gather some data. These numbers are very well separated. If it was 3.913 and 3.915, I might have to run so many simulations that it would be hard to really distinguish the 2 and conclusively determine which is going on. For a lot of the effects of general relativity, the effects were very small refinements to theories at the places that we could observe, that it was very hard to numerically confirm general relativity at first. But here, basically 4% to 6%, that's a significant difference. If we run 1,000, 1,000,000, 1,000,000,000 simulations, we will see which way it's clustering. And what we'll see is it's actually clustering around these 2. These 2 ones are correct, the third one is wrong. And the reason it's wrong is each trump card has a 50-50 chance of being in each hand. But as soon as I start giving you some of the trump cards, your hand is filling up. And it becomes less likely for you to get additional ones. If you imagine the ridiculous situation where there were 14 trump cards, and each card had a 50-50 chance of being in each hand, there's no way you could get all 14 trump cards when you only have a hand of length 13. It's got to break down at some point. And so it can't keep being 1/2, 1/2, 1/2, 1/2. So the reason I was playing ABBA at the start of class is not just because it's a wonderful group, but because ABBA illustrates a wonderful concept. So I will not even try to say their names aloud. There are 4 people in ABBA, and they were married in groups of 2, and then they were divorced in groups of 2. So I will just call them A1, B1, B2, and A2. And I will be careful because this is being recorded, but we will just say that the divorces were not they're not going to be held up as examples of how to have divorces in the future. If I ask you a question, how many ways are there to choose 2 people from ABBA to form a group of 2, a subgroup of 2? How many ways can you do that? 4 choose 2, which is 6 groups of 2. Is everybody equally likely to be chosen if I do this? All right. Can you give me, if I'm forming a group of 2 from ABBA, what might I want to make sure I don't do? Yeah, void A1 and B1 and? B2. Yes. We'll assume A1 and B2 are fine being together and B1 and A2 are fine being together. That may not be the case. I'm not going to go into this level of detail on ABBA. I've heard that they were offered at one point $250 million to get back and tour and said, no thank you. We've got enough money. We really don't want to get back together. So now we will consider A1, B1 new. We will consider A1, B2. We will consider A1, A2. We will consider B1, B2. And we will consider B1 and A2. Now there are only 4 groups of 2. Is everybody still equally likely to be chosen? If you look at A1, A1 is chosen half the time. A2 is chosen half the time. B2 is chosen half the time. B1 is chosen half the time. Everybody is still equally likely. So when I say I want to choose a group of 2 people from 4 with everybody equally likely, this actually still satisfies that. If I went to the ridiculous extreme of just A1, A2, and B1 and B2, everyone is still equally likely to be chosen. You've got to be very careful in terms of what problem you solve and listen to how it's being stated. So there's a lot of conditions. Given that you will not be with your ex, what's the probability that B1 is chosen? It's still going to be 1/2, but it's a very different 1/2 than in this case. So this is going to lead us to the idea of conditional probability. So the first 2 arguments here are correct. This one here is breaking down because as you keep adding each one is independently, each card has a 50-50 chance of being in either hand. But all 5 cards, it's not 1/2 to the 5th. Just like as soon as I tell you we've chosen A1, what do we know? B1 is not going to be present in that subgroup of 2. Okay? So let's go back and let's do another problem. Is there anybody here who has not, I think I've asked this before, who has not played a game with die where you roll die, like Monopoly? You have 2 die and they have the numbers 1 through 6 on them. And for the most part, you assume the die are independent. That all numbers are equally likely. All right, so we have 2 fair independent die. Is it dice? Dice. We have 2 of them. So the question, what is the probability the sum is an 11 or a 7? So what's the probability I roll an 11? What would be the probability that I get an 11? 2 over 36. I can get a 6 and a 5, or I can get a 5 and a 6. What's the probability I get a sum of 7? 6 out of 6. You get a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, a 6 and a 1. Okay, now the first die is a 3. Same questions. What's the probability you get an 11? Yes. 0. There is no way you can legally, legitimately roll a sum of 11. I'm sorry? Oh, yes. Interesting. Thank you. So there's no way you can roll a sum of 11. What about a sum of 7? It's still 1/6. And the reason is, once you roll the first die of a 3, one and only one number will work and will always work. So in this case, if I tell you you rolled a 3, no additional information is provided. It doesn't change your calculation of what's the probability of getting a 7. This is a dinky example, but it illustrates what's going on. In this problem, boy, does it provide a lot of information. As soon as I know we rolled a 3, there is no chance that we can roll an 11. So the idea of conditional probabilities is, if you know something about what's going on, that can influence your calculation of the probability. What do you think the probability is that my son's soccer team will win their next game? 100%. If it's Williamstown soccer, yes, actually that is correct. I think the only time they've lost are days when they've had so many players not show up that they haven't been able to field a full team. And even those games have been close. But in general, what's the probability a team wins? What would you like to know? Yes?
Who is the team?
One is how good is the team. What else might you want to know?
It's the opposite.
How good is the opposition? If I tell you, we are playing this year. Any Baltimore fans here? Okay. If I tell you we're playing the Baltimore Orioles, who have lost well over 100 games, that's very different than if I tell you we're playing the Houston Astros. And so the answer is going to depend. This is a great example of conditional probability. And so what we want to do now is we want to try to figure out what is the probability of an event A given that some other event B has happened. And sometimes knowing B has happened will give you no information at all about A. That will be an independent situation. Other times, knowing that B has happened will give you tremendous information about whether or not A happens. That's what's going on here with the sums of the die. So again, you always want to have extreme, ridiculous cases to just test what's going on. So rather than just immediately writing down the answer, I want to spend some time sniffing out the formula. So conditional probability. So we want the probability of A given B. So this means B happens, or given B happens, what is the probability that A happens? Okay? And let's guess that this is some function of the probability of A and the probability of B. We did this before when we were trying to find what's the probability of A union B. We tried to sniff out what that formula was. Given how successful that was, let's see if we can do that here. It might turn out that this will not give us enough information, that just using probability of A, probability of B is not enough. What would be a really good choice to take for either A or B?
1 or 0.
Okay, so either the entire space omega or the empty set. And there's another relationship between A and B that might be useful.
Mutually exclusive?
I'm sorry?
Mutually exclusive, so they both get that complement.
Yeah, complement. So I think good case, case 1, A equals B, and case 2, A equals B complement. Now, if I believe that the conditional probability depends only on the probability of A and the probability of B, let's make them both the same. Right? What would be a good value to make both of those probabilities? 0.5. And then what's the probability of B complement? So in this case, if probability of A equals probability of B equals 1/2, then we would have f of 1/2, 1/2 for this one, and we would have f of 1/2, 1/2 for this one. But what's the probability that A happens, given that B happens, if A is B? I'm sorry? So what's the probability that A happens given that B happens, given that B is the same as A? It's 1. This is almost the easiest question I can ask you. Given that I like the Red Sox, what is the probability that I like the Red Sox? Given that I hate the Yankees, what is the probability I like the Yankees? 0. So in this case, you get the probability of A given B is 0. So this quick analysis tells us that whatever the formula is for conditional probability, it can't depend on just the probability of A and the probability of B. It can't be something like the probability of A divided by the probability of B. That's not going to work. It's got to be more complicated. So again, I really like the idea of trying to sniff out what a formula might be rather than just quickly writing it down. You want to build intuition, and then as the problems get harder, you want to learn how can you look at extreme cases. So there was a math riddle that I was discussing with a Williams alum. He was back on campus for various things, and he had gotten this on a job interviewing question. And the way they phrased the problem, they gave information away. They gave that no matter what the size of the table was, somebody had a winning strategy. The same person, in fact, had the winning strategy. And he said, well then if I look at this extreme case, it's very clear who has the winning strategy, so there must be the winning strategy in every case. Or at least I know the player who has the winning strategy. Sometimes you can look at small cases, especially in job interviews, and gain something. So I will try to include what that problem was in an email to you later and see if you can figure out what it should be. So now let's try the probability of A given B is a function of the probability of A, probability of B, and then the probability of A intersect B. And I claim A intersect B is the next natural thing to try. And the reason A intersect B is the next natural thing to try is what does it mean for A to happen given that B happens? It means both events happened. And that's exactly what A intersect B is representing. A intersect B represents both things happened. All right, I'm going to have to do something because this is getting really moving. All right. So now, I won't go through all the derivations, but after a while, you're led to maybe it's the probability of A intersect B divided by the probability of B. So you can get there by trying lots of special cases. You can try cases where A equals B, where A equals B complement, where B is the entire set. One thing you want to stay away from is the probability of B is 0. Why would you want to stay away from the probability of B is 0? So one thing is it's the denominator here, but we're just guessing that this is. At a higher level, when we're trying to figure out the probability of A given B, why can't we look at sets B with probability 0?
B doesn't have it.
Yes. Given that my professor likes to murder people late at night and bury the bodies, what's the probability we will have a surprise quiz tomorrow? Okay? Hopefully this is a situation where that event does not happen. And so you're not going to be able to analyze this case. We are only going to analyze cases where B does happen. In the words of the great George Carlin, anybody hear his airline routine? One of my kids' favorite parts is, when you land, the airline attendant says, please check your immediate seating vicinity for any items you may have brought on board. And George Carlin goes, I may have brought on board my grand piano, but I didn't, so I'm not going to look for it. I'm going to look for the items I did bring on board. It's the same thing here. We're not going to talk about the conditional probabilities when B doesn't happen. So always we will have the probability of B is greater than 0 when we're doing conditional probabilities. This actually suggests that a better thing to study is the probability that A and B happen is the probability that A happens given B times the probability that B happens. Now we have no division by 0, and that's a much better object to look at. If you want, view this as here's the universe omega, here's your set A, here is B, and here's A intersect B over here. And so if we want to look at what's the probability that A happens given B, well, I've now reduced my universe to just over here to just B. And so essentially what I now have to do is, maybe initially B only had 80% chance of happening, but now I have to reduce my discussion to reassign probability so that now B happens with probability 1. That's going to essentially rescale things. And then that will rescale the probability that A happens. Yes?
Could you try making the remote like vertical to the thing?
Absolutely. Thank you. We will see if that works. But, well, all right. Well, that seems to be working right now. So if this works, you can email me for extra credit, for technological extra credit. All right. Let's do an example. So I will try to do the same example in the book. So we have the following. You catch at most one fish per day. Once you catch a fish, you stop fishing. You have a 40% chance you catch a trout. I think it was a 25% chance you catch a bass. Yes. And then you have a 35% chance that you get nothing. And we want to calculate what is the probability you catch a trout given that you catch a fish. Okay? So one way to do this is to imagine we do this day after day after day and keep track of what's going on. So we did this 1,000 times. How many times would we catch a trout? 400. How many times would we catch a bass? 250. And how many times would we catch nothing? 350. A trout, a bass, nothing. And again, I chose 1,000 because with all these probabilities, if I multiply, 0.4, 0.25, 0.35 by 1,000, they'll all be integers. I didn't have to choose 1,000, what would have been a better number? 100. You could, of course, do a number like 747, and you would have fractional amounts, but it would make the algebra a little bit harder. It's nice, and I like to put an extra 0 sometimes just to make sure if I'm tired, I haven't done a calculation wrong. This is catch a fish. And this happens 650 times. So we can calculate now what is the probability we catch a trout given that we caught a fish. We can look at this tree of probabilities. So for this one, probability catch trout given we catch a fish, this is going to be 400 over 650. I can write that as 400 over 1,000 divided by 650 over 1,000. And this is the probability of catch trout over the probability we catch a fish. The reason I'm doing this is everything is right, but this is not necessarily going to generalize correctly. We wanted the probability of A intersect B divided by the probability of B. This is just the probability of A divided by the probability of B. It really should be the probability that we catch a trout given that we catch a fish. I'm sorry, it should really be the probability we catch a trout and we catch a fish. So we want probability catch trout and catch a fish divided by the probability we catch a fish. Right? This is A intersect B. This is just A. Yes?
Is it because
Yeah, A is a subset, because in this special case, A is a subset of B. So there's no way you can catch a trout without catching a fish. So in this case, here is omega, here's B. A is entirely contained in B. So in that case, A intersect B is just A. The reason I wanted to do this is to just remind you of the danger of looking at special examples and generalizing. We've done the 16 over 64 in this class. Right? Yes, the fraction. So just because it works a couple times doesn't mean it always works. So this is an example where you might think it's just probability of A divided by probability of B. No. In this case, it does come out that way. All right. So now we have handled the case of the trouts. We have seen what's going on. We want to now generalize a little bit more about what we mean by conditional probabilities. We have at least a formula that will allow us to calculate things. And then we want to see how far we can push this. So conditional probability. All right. So we know the following. If the probability of B is greater than 0, then the probability of A given B is the probability of A intersect B divided by the probability of B. We can rewrite this as the probability of A and B is the probability of A given B times the probability of B. This is a very reasonable way to look at things. What's the probability that A and B both happen? It's the probability that B happens times, given that B has happened, A also happens. All right. Instead of looking at the probability of A intersect B, what's a nice related quantity we could look at? Sorry?
A doesn't happen?
We could do that, but something that's really closely related to A intersect B. Maybe even the same as A intersect B. B intersect A. What's the probability of B intersect A? It's the probability that B happens given that A happens times the probability A happens. Well, these sets are the same, so these probabilities are the same. Who knows what rule we are leading up to? Bayes' rule. So how about you've taken a stats class where they have the Bayesians versus the frequentists? All right. We're not going to get into a dispute between those two philosophical approaches in this class. All right. I will take a just descriptive approach, and I will say other classes will will talk in greater detail about Bayes' rule. But from this we can actually solve, right? And we can now get the probability that A happens given that B happens, well, these are all equal, is going to be the probability that B happens given A times the probability of A divided by the probability of B. And the whole point here, I'll call this Bayes' rule, or at least one form of Bayes' rule. Oh, I'm sorry. That's putting in personal preference. I'll still. Why is this useful? It all comes down to what information do you have. And this is why I wanted to spend, or one of the reasons I wanted to spend some time earlier today talking about sniffing out a formula. What inputs could go into calculating a conditional probability? If I think that the only inputs are the probability of A and the probability of B, we quickly see, no. There's no way that can be enough. We need more than just that. All right, how much more do we need? And we saw, well, we need the probability of A and B, A intersect B. Sometimes some information is easier for you to get than others. If I know the probability that B happens given A, and the probability of A and the probability of B, I can easily get the probability of A given B. The other one would be the probability that B happens given A is just the probability of A given B, probability of B, probability of A. Well, these two fractions of over here, the last part, they're just inverses of each other. There's no real difference in calculating this or calculating its reciprocal. But this, there's real difference. sometimes it's much easier for you to get data of B happening in the subset where A happens than it is to get data of A happening in the subset where B happens. And the idea, yes? Okay. So it all comes down to which information do you have readily available. Okay? If you have information of one, you can use that to get information of the other. And so the book goes through, I think, some really good examples. I think it talks about, is it tuberculosis? Is that the example that's done? Of you're trying to figure out, maybe is it false positives? This is a huge issue in the medical industry. If you are tested for a very bad, life-threatening disease, and a test comes out positive, what should you do? Worry. Get tested again. And you really want to know, how worried should I be? Which is, I'm trying not to use value judgments, but I don't know how to do this without using value judgments, so I'll use value judgments. For society as a whole, which do you think might be better? Telling a few people you have a deadly disease and you're going to die in the next week, and then turn out later, oh, whoops, actually we were wrong, you're fine. Or not telling somebody that they're going to die in a week unless they get some very expensive medical care. Is it better to not tell somebody that they have a very bad disease that can be cured, or to have somebody worry needlessly for a few days? I think most of us will agree it's better to have a couple people worrying needlessly than to not tell people who are very sick that you need some treatment now. So when you're trying to decide how to design your tests, not all errors are equally likely. You've seen stuff like this before in elevators or bridges. It's much better to have the elevator or the bridge not have as much of a carry load in it as it could take than to accidentally put too much in because the effects are catastrophic. So it's, which way do you build things? For a lot of tests, it's much better to just tell people, you know what, you should be tested again. Now, if you're the doctor, what might you tell somebody? If the test comes out positive and they've got this life-threatening disease, what might you tell them? You definitely want them to be tested again. Will you tell them you've tested positive for a disease that will kill you unless we give you some very bad, painful medical treatment? What might you tell them? Yes? Tests were inconclusive. Unfortunately, the test we didn't get a good result, so we're going to have to test you again. Now, the other thing is, you might have different levels of tests. You might have a very expensive test that if you think somebody now might have it, now you give them the really expensive test, which is very accurate. This is a great way to deal with finite resources. So there's a lot of great problems related to this, a lot of really good problems in medical treatment. So I strongly urge you to read that section of the book and really think about how you want to deal with stuff like this. Okay? But definitely stuff like this is done. You have to manage patient expectations. One of the hardest parts is to make sure patients actually take the tests that they need, or take the treatments that they need, or go and see the doctors. What can you do to do this and maybe not have them freaking out? Yes?
I had a question about Bayes.
Yes.
Because I've asked, I think, 2 other professors about more intuition, and the best
Okay.
they've told me was we'll make a tree diagram or just plug
Right.
in values, and that was
Right.
kind of the extent of the intuition.
Right.
So I was wondering if maybe you had something better than draw a tree diagram.
I mean, to me, I always think of it at this level, that we're just looking at something 2 different ways. What we're really studying is the probability that A and B both happen. And the probability that A and B both happen can be given in either of these 2 expressions. And then the whole point of Bayes' rule is to go from one direction to the other. So I don't know, you should not publicly say right now whether or not that was a better explanation than you've heard otherwise. But if I do hear from some of my colleagues in future years that you are again asking this question, no. Any other questions on this? There's a lot of really good paradoxes in the subject. Later we might get to, I think it's called Simpsons Paradox. Have any of you done this? I think the example that's often used is Derek Jeter, who's one of the few good Yankees, and I think David Justice. That in each year, David Justice had a better, in 2 years, in each of the 2 years, David Justice had a better batting average than Derek Jeter. But for the 2 years, Derek Jeter actually had a better batting average. This has also been used in looking at whether or not graduate programs are discriminating in which students they accept. And so later in the semester, we might actually return and study something like this. All right, any other questions on Bayes? All right, so we've got about 10 minutes left. So what I want to end with is the theory of partitions. We've already done a lot of stuff with partitions. This is going to now just make it a little bit more formal. All right, so for the theory of partitions, we say a set BI partitions omega if the following three things happen. The set is at most countable. What this means is that either we have only finitely many elements in a set, or if we have infinitely many, it's the smallest infinity possible. It's in a one-to-one correspondence with the natural numbers. We are not allowing ourselves an uncountable thing. All right. I'll let you tell me what you think the next one would be. If we wanted to partition omega, what should be true? Yes?
The union of intersections become another space or something.
Okay, not the union of the intersections, you're close. Just the union. Right. We're trying to partition, we're trying to break up omega into places. So we want the union over the I of the BI to be omega. And what's the last thing we want to be true?
The intersection of any of the partitions should be empty.
Good. So you want pairwise disjoint. So BK intersect BL is empty if K does not equal L. There's no elements in common between two things. So, going back to our picture, here is the universe omega. Here's maybe B1. Here's B2. Here's B3. How much time do I have to fill up? B4. B5. And now maybe here's B6. B7, and maybe I'll just do infinitely many lines like that. Each one is going half the distance. So this would be a partition. Okay? All right. So now, why is this useful? Well, this is going back to what we did on the very first day of class. When we had the shootout between Bird and Johnson, we wanted to calculate what is the probability Bird wins. Well, we took what's the probability of Bird winning, that event, and we split that event up into disjoint places. What's the probability he wins on his first shot, second shot, third shot, fourth shot? So we're really partitioning all the games into games that end after one shot by Bird, games that end after two shots by Bird, games that end after three shots by Bird. Or even more generally, just games that end after one shot, two shots, three shots, four shots, five shots. And then seeing for each one of those, what's the probability Bird wins? If the game ends after an even number of shots, we know Magic was the last shooter, and therefore the probability of Bird wins is 0. We know that if the game ends after an odd number of shots, Bird was the last shooter, and the probability is 1. So if I tell you, this is a great example of conditional probability, that in the Bird-Johnson alternating shootout, the game ends after an even number of shots, you know with 100% certainty that Magic won. Conversely, if you know that the game ended after after an odd number of shots, you know with probability 1 that Bird won. So the probability of A is the probability of A intersect B plus the probability of A intersect B complement. We've seen this before. This is the simplest partition of a set omega. We're partitioning omega into two sets, B and everything not in B. Right? We can generalize this. And if you want, one way you could generalize this is I could partition into B1, and then B1 complement is everything else. And then I'll take B1 complement is B2, and then everything else. And I can just propagate this downward. So we get the probability of A is the sum, I goes from 1 to infinity, the probability of A intersect BI, where the BI's are partition. And this is just a natural generalization of what we did up above. Well, we can use our conditional probabilities, right? What's the probability of A intersect BI? This is the sum I goes from 1 to infinity of the probability of A given BI times the probability of BI. So this is a really good way of calculating things. What's the probability I'm in situation BI? And then what's the probability I happen given that I'm in situation BI? Okay? So this is a terrific way of calculating probabilities. It all comes down to what information is easy to get. Intersections are easy. Unions are hard. Right? This is the general rule. Intersection is better than union. Okay? So we have a few minutes left, so I will start doing a little bit for the next lecture and start training a little bit about how we will start dealing with the inclusion-exclusion principle. Right. How many of you have taken discrete mathematics, out of curiosity? At a decent number. How many of you have seen the inclusion-exclusion principle? Okay. So the idea is we want to keep track of how things can happen. So the inclusion So I want to calculate the probability someone gets all of a suit in bridge. So I have 4 people. Each person gets 13 cards. Each suit has 13 cards. And I want to know what's the probability that at least one person has all cards in a suit. This is really bad. So we could let AI be the event person I is 1 suited. What event do we want to calculate? Yes?
The union.
We want to calculate the union. We want A1 union A2 union A3 union A4. Does this mean everybody is 1 suited? No. This means at least one person. These are hard things to do. What we do by inclusion-exclusion is we look at A1 intersect A2 intersect A3 intersect A4. What would that be? All of them have 1 suit. That's easy to calculate. But that's also nowhere near the right answer. Right? But that's easy to do. It would also be easy to do just 3 of them are 1 suited. Or 2 of them are 1 suited. Or 1 of them. Now, what we can do is the following. The probability of the union of the AIs is going to be the probability, the sum, I goes from 1 to 4, of the probability of AI. So I'm going to treat them as disjoint events. The first person is 1 suited, the second person is 1 suited, the third person is 1 suited, the fourth person is 1 suited. This is a great way to start. And I'm just going to add all the probabilities. Why can't I just add all the probabilities?
You overcounted by the events where more than 1.
Right, so now let me subtract the sum I and j. I does not equal j, the probability of ai intersect aj. So now, if both player I and player j have one-suited hands, I subtract off one here, and I've added two over here. And now I'm in great shape. Oh, what's the problem? If there are three people who are one-suited, I would count them 3 times here. Say it's people 1, 2, and 3, and then I would subtract 3 times here. So I then add back some I, j, k, distinct, P of ai intersect aj intersect ak. And then what's the last thing I have to then subtract back? A1 intersect A2 intersect A3 intersect A4. So this is the theory of inclusion-exclusion. We'll do a lot more with this, but this is just a quick way to start. And this is breaking up unions into intersections. The idea here is I would much rather do an easy problem many times than one hard problem. And so the intersections are much easier to do. We've got rules to deal with intersections. All right, this is a good place to stop.